This next lesson is how does current and voltage behave in series and parallel circuits. First of all, what is a series circuit? A series circuit is this. Okay? Now, a series circuit, think of a TV series. Okay? What do you have in TV series? You have loads and loads of episodes and loads of seasons. So in this TV series, this is quite a boring TV series. We've just got one episode. Okay? But this lamp is connected in one line, okay, or one loop, okay? And the clue to knowing the difference between a series and a parallel circuit is that a series circuit will always have one loop, and that loop can contain as many devices, electrical components you want to put on it, okay? So if I did add another lamp like this, then I can say, okay, episode 1, episode 2. But the loop, or in a TV series, it will always be one story, okay? So that's how you can remember what a series circuit is. What about a parallel circuit? Okay, a parallel circuit is connected like this. Okay? Okay, if we're going to move on from our analogy of TV series, think about parallel worlds or parallel universes. Okay, if you're a science fiction fan. What is a parallel world? Well, basically, it's a world which coexists during the same time as another world, okay? So in this case, electrons are going to be sent from this end of the battery or cell, and then they're going to split, okay? Half of them are going to go down this way, and half of them are going to go down this way, okay? If these two lamps are the same size, and they're bought at the same time, okay? So they have the same resistance, electrons are going to split half and half, okay? But the electrons, as they pass through this lamp, electrons are also passing through this lamp, okay? So in our analogy of parallel worlds or parallel universes, things are happening on both of those worlds at the same time, okay? Or if you want to think about parallel railway tracks, these lines are parallel to each other as well, okay? So that's the way you can remember the difference between them. How does current behave in a series circuit? Okay, if I put an ammeter here, okay, and if I put another ammeter here, okay, now these aren't drawn the best, they should actually be in between. In fact, let me draw this again properly, okay. So I'm actually going to put 3 ammeters in this series circuit. Now, if I told you this first ammeter read 2 amps, this would also have to equal 2 amps, and this would also have to equal 2 amps. And the rule in a series circuit is current always is the same no matter where you put the ammeter in the series circuit. Okay? Also, when you connect a ammeter in a series circuit, make sure it is in series, okay? It is in between the wires, okay? It is not connected parallel like a voltmeter, okay? Which I will show you in a second. What about in a parallel circuit? So this time, I'm going to add an ammeter here, okay? Another ammeter here, another ammeter here, and here's my lamp, okay? Okay, and they're going to connect back to the original circuit like that, okay? Now, if I told you this was 2 amps here, remember I told you the current splits up, okay? Now, if current is measured in amps and current splits up, this is going to read 1 amp and this is going to read 1 amp as well, okay? If I drew another ammeter here, okay, this would then read 2 amps because the current would join up again in this loop, okay, and it'll go back to the battery, okay. You could think about it as water pipes, okay. This will be a thicker water pipe, then it splits into 2 thinner water pipes and then connects back to a thicker water pipe, okay. So what is the rule? Well, current is the same in a series circuit and it splits up in a parallel circuit, okay. Okay, now let's look at voltage. So what about voltage in a series circuit? Now notice how I connect up my voltmeters. I connect them up in parallel. And I connect them up at 2 points. Okay, so electrons are going around this way. Okay. So the difference between conventional current and the direction electrons travel at. At this moment, you can see the minus signs, okay, going around. So that's the direction that electrons travel at. However, if I change the setting, the arrows are now going the opposite direction, and that's showing the conventional current, okay? And for historical reasons, conventional current was thought of because they thought the charge was positive, and therefore they thought charge went from the positive direction to the negative charge, to the negative plate of the battery, okay? But you just need to be aware of the difference. Conventional current goes from positive to negative, whereas the direction of electrons go from negative to the positive end of the battery. What is happening? Electrons have got loads and loads of chemical energy from the battery. It's being transferred into kinetic energy, okay, and electrical energy as it travels around the circuit. Now, once it reaches, it has to get to this positive end, okay? This is the negative end, and this is how electrostatics works, or electricity works. The electrons are attracted to this positive end of the battery. The only way they can reach this positive end is if they travel around this circuit, okay? However, it's got two major obstacles to overcome, okay? And we can think of these as like little mountains, okay? But the electron still wants to get to the positive charge, okay? And it doesn't mind going over these mountains. However, each time it goes over these mountains, it loses some energy. Okay, so the analogy I want you to think of, let's say you're at home, okay, and you have to get to school. Okay, you have 2 mountains, okay, to pass over. Okay, but you have to get to school, otherwise you get into trouble. Okay, so you've had your big breakfast, you've had a good night rest. Okay, you got lots and lots of energy. And also, I'm going to give you credit, you're also quite smart, okay? And you know beforehand you've got 2 hills to get over, okay? So you make a calculated decision that you are not going to use up all your energy on the first hill and run up it really quickly so that you literally have no energy to go up the second hill, okay? Because that will be not wise and you won't get to school. So you make a calculated decision, I'm going to roughly use half my energy on this hill and on this hill. Okay, and that's what you do. Okay, you go up this hill with a moderate amount of energy, or half energy, and the second hill with the rest of your energy. And that's what happens with electrons. The electrons, let's say this was 6 volts, okay, 6 volt battery. The electrons carry 6 volts as they travel around. It knows there are 2 mountains or 2 bulbs, and it has to pass those 6 volts onto both bulbs before it reaches the other end of the battery. Okay, so it does that. And how does it do that? Well, it does that equally so that this voltmeter reads 3 volts and this voltmeter reads 3 volts. Okay? How does it work in a parallel circuit? So if I quickly draw the bulbs like that, okay, voltmeter here, okay, and just I forgot to mention it's connected at 2 points because the voltmeter is reading the amount of energy or voltage the electron has before it reaches the lamp and after, okay, before and after, and it works out the difference. That's why it's called the potential difference. Okay, what's happening here? Same battery, 6 volts, but this time this reads 6 volts and this reads 6 volts. And actually, if you did this experiment, and I'll show you in a later video, in a virtual circuit builder application, that the brightness of these 2 bulbs is actually brighter compared to these 2 bulbs, okay? And the reason is because each bulb has 6 volts measured across it, okay? And basically what's happening now is our analogy of you leaving home to school. This time we've extended it or expanded it to have more students leaving home and getting to school, okay? So this time the battery is sending out loads and loads of electrons, okay? It does send out loads and loads of electrons here, but in this case, if we actually put an ammeter here, there would be actually more current passing through this point compared to this point in this circuit, because the battery has to push more electrons to pass through these two pipes to give it's just got greater distance to cover, essentially. Okay, it's not the fact that there are two mountains, but the pathways to reach this mountain and the pathway to reach this mountain is just more distance to cover. Okay, and basically one electron can pass through this point, one electron can pass through this point. Okay, but each electron has got 6 volts, so electrons are coming down here, donates or not donates, passes its 6 volts of energy here, goes back to this positive end of the battery. Another electron goes down here, 6 volts, passes to that end of the battery. Okay, and this happens really quickly, very quickly, and at the same time electrons are passing through these lamps at the same time. Okay, but what is the rule? Voltage is shared or split in a series circuit, and voltage is the same across the electrical components in a parallel circuit. Okay, so they're basically the opposites of each other. Okay, so if you remember, in a series circuit the current was the same throughout, but in a parallel circuit the voltage is the same across each branch. Okay, however, in a series circuit voltage is split. In a parallel circuit, current is split. Okay, so if you remember it that way, you can't go wrong. Okay, and that's the end of this lesson.